Welcome to this next lecture on vibrations of plates and shells. In the last lecture, this is where we left off. We parameterized the this general curve in terms of its arc length, and we went ahead and found the unit tangent vector, which is dr ds, and we were going to look at the curvature and the radius of curvature. So let me just directly tell you that the curvature vector denoted as t dash is dt by ds. Okay, this is curvature. Okay, now I will just give you a physical argument in the sense that we have a unit tangent vector that is moving that way. Okay, and so any change on that will be perpendicular to curvature. I mean perpendicular to the tangent. Perpendicular to t, and therefore it will lie in this direction. Okay, that is the curvature vector. Okay, now without going so much into differential geometry, if this is a very simple curve, okay, without doing twists and turns, okay, like a part of a circle, okay, a circle is vertically placed part of a circle, then this plane is called a osculating plane. Osculating plane. Okay, as I said, I am not going too deep into that. So this tangent vector and this curvature vector, they will lie in this osculating plane. Okay, there is also another vector called the binormal. Okay, at this point there is another vector called the binormal. Okay, so they are kind of denoted by t, n and b. Okay, not in the same sense, they are denoted in the sense of a right handed coordinate system. I am just telling you the directions. Okay, we have to set a convention for the normal. Okay, so we have to set a convention for the direction of this. Okay, now before we do that, let me just take the same or a similar simple example so that you are convinced. Okay, so the example is a simple circular arc or circular curve, 2 cos t I plus 2 sin t j plus 0 k. Okay, this is a circle. The circle with radius 2, radius magnitude 2. Okay, that much we know. Let us see. So if we find the tangent or dot of t, that is minus 2 sin t plus 2 cos t, hold on, 2 sin t I plus 2 cos t j plus 0 k. Okay, and what is the magnitude? Magnitude of r dot is equal to root over 4 is equal to 2. Okay. So what I have here is a circle with a radius 2. Okay. So what is arc length? Arc length S is given by integral t equal to 0 to t twice du is equal to 2t. Okay. And therefore, if I parameterize it in terms of the arc length, my r hat of S now looks like twice cos S by 2 I plus 2 sin S by 2 j plus 0 k. Okay. Now we spoke of the unit tangent vector, okay, which is dr ds. So if we compute dr ds, which is r hat dash of S, that is equal to minus 2 sin S by 2 into half I plus 2 cos S by 2 into half j, that is all, which is equal to what? I cancel this, minus sin S by 2 I plus cos S by 2 j, that is my r dash. Okay. And the curvature, okay, this is my tangent, curvature is t dash, okay, which is equal to r hat double dash, okay, that is my minus half cos S by 2 I minus half sin S by 2 j. Okay. And what is the magnitude? Magnitude of this is equal to half magnitude of the curvature vector. Okay. And the inverse of this, inverse is gives you the radius, which is 2. Okay. Now let us just see that S equal to 0 is over here, S equal to 0 is over here, okay, S equal to 0 over here, and this is quarter of it. So what is the arc length? The total circumference is twice into pi into r, which is 2, which is 4 pi, and a fourth of it is equal to pi. That is the arc length. That is the arc length till here. Okay. And so now at s equal to pi, if I compute my curvature, okay, I get r hat double dash s is equal to minus half cos pi by 2, which is 0, and sin pi by 2 is 1 minus j. Okay. And so points downwards. Okay. Now here, if I decide to write r double dash of s as a curvature magnitude into a normal where n is the principal normal, okay, that lies in the osculating plane. Why we call it a principal normal? If I have a curve, this can be the tangent, but it has infinite normals. At that point it has an infinity of normals. So we call that particular one in the osculating plane as the principal normal. So if this principal normal, we have a convention that it points away from the radius of curvature. Okay, it points away from the radius of curvature, then the curvature vector and the principal normal are opposed. Okay, r dash of s and n are opposed, in which case kappa will be a negative quantity. Okay, you can see that r double dash of s turned out to be minus j. Okay, and in this convention over here, in this convention, the principal normal is upward, away from the radius of curvature, upward, which is actually j. Okay, it's actually j. So now what happens is, if this is my principal normal n, then this is k, which is going to be negative, or which is going to be kappa. Kappa is negative. Okay, whereas if we set both conventions to be same, that means r double dash of s and n are in the same direction, same sense, then this will be positive. So we will use this convention. Okay. Now this is as far as curves is concerned. Okay. We have to start now looking at surfaces. We have to look at surfaces. Okay. For we will be looking at vibrations. Okay. And as mentioned in the introduction of thin plates and shells, And by what do we mean by thin? That means the other dimensions are much bigger than the thickness dimension, h the thickness dimension. So for example, if I have a rectangular plate, then I have this as the plate, and this is the thickness. Okay, that's what I mean by thin plate. Now, as a rule of thumb, okay, the thickness over the radius of curvature must be less than 1/20, okay, or h is less than r/20. R is the radius of curvature. So if I have a curved section, let's say, and the radius of curvature is, this is the radius of curvature, then the thickness should be such that it follows this rule of thumb. That's a rule of thumb. Okay. And further these media, okay, the shell or plate have a middle surface, well defined middle surface. Okay, and we will first describe properties related to the middle surface. So how do we define a point on the middle surface? So I have a coordinate system, my orthogonal basis, which is, let's say, E1, E2, E3, okay, and let's say there is a surface parameterized in terms of alpha 1, alpha 2, okay, and we want to describe points on that. So there is a point P and there is a vector describing the point. Okay, so how do we describe it? This point R on the surface parameterized by alpha 1, alpha 2 will be given by the vector R at alpha 2 is some function alpha 1, alpha 2 E1 bar plus F2 alpha 1, alpha 2 E2 bar plus F3 alpha 1, alpha 2 E3 bar. Okay, or sum x1 E1 bar plus x2 E2 bar plus x3 E3 bar. Okay. The next step is I would like to describe a differential vector length, a differential vector length or differential vector dr alpha 1 alpha 2. Okay, it's quite simple. Dr alpha 1 alpha 2 is equal to del r by del alpha 1 d alpha 1 plus del r by del alpha 2 d alpha 2. Okay. Now, so pictorially what is it? I have this is point here P as a point here P dash, let's say. Okay, and let's say my alpha 1 moves like this, alpha 2 moves like this, and I want to describe this vector dr, and from there the length, differential length. Okay, so what do we want? We want ds, let's say square, which is dr dotted with dr. Okay, so how will that look like? My ds square looks like del r by del alpha 1 dotted with del r by del alpha 1 d alpha 1 squared. I am just dotting, taking a dot product of this vector with itself. Okay, so if I continue, plus del r by del alpha 2 dotted with del r alpha 2 d alpha 2 squared plus 2 del r by del alpha 1 dotted with del r by del alpha 2 d alpha 1 d alpha 2. Okay, so we'll give this the symbol E, this the symbol F, and this the symbol G. Okay, so this is called the first fundamental form. First fundamental form. Okay, now we will show by an example that here del r by del alpha 1 points in the alpha 1 direction, points in the alpha 1 direction. Okay, similarly del r by del alpha 2 points in the alpha 2 direction. We will show that through an example. Okay, so now what happens if we have an orthogonal curvilinear coordinate system. That means the angle between alpha 1 and alpha 2, wherever you place your coordinate, is 90 degrees. Okay, and because del r by del alpha 1 points in the alpha 1 direction, del r by del alpha 2 in the alpha 2 direction, the dot product of this will be 0. This will be 0. Okay, so we are left with E and G. So my ds square looks like del r by del alpha 1 magnitude squared d alpha 1 squared plus del r by del alpha 2 magnitude squared d alpha 2 squared. So we will give these further symbols in this form. We will call them as a1 squared d alpha 1 squared plus a2 squared d alpha 2 squared, where a1 and a2 are called the Lamé parameters. Okay. So for orthogonal curvilinear coordinates, this is the first fundamental form. Okay. Now let us look at some examples. Okay. So let us look at a plane. Here is my rectilinear coordinate system x, y, z. Okay. These are my alpha 1, okay, that is the basis. Okay. Then I will have alpha 1 as x and alpha 2 as y, and I will describe a plane that is parallel to the xy plane, okay, normal to the z axis. Let us say this is z equal to z0. Now I want to describe a point on this plane, point P. Okay, so what is the description? R x comma y is equal to x I hat plus y j hat plus z0 k. Okay, so it is independent of z. So what is now dr x comma y? It is del r by del x dx plus del r by del y dy. Okay, what is del r by del x? That is I. Okay, and what is del r by del y? That is j. Okay, so what is my a1 square? That is equal to del r by del x dotted with del r by del x, which is also magnitude of del r by del x squared. It is equal to 1. It means a1 is equal to 1. Okay. Similarly, what is a2 squared? What is a2 squared? That is equal to del r by del y dotted with del r by del y, which is magnitude del r by del y magnitude squared, which is also 1, implying a2 is also equal to 1. Okay. So what is my fundamental form? ds square, which is dx squared, there is a 1 here, plus 1 dy squared. Okay, for a simple plane. Okay, so Next example, let us take a circular plate, circular flat plate, okay. So this is my circular plate, this is my center, okay. Let us say this is my x, that is my y, and that is my z, okay, and I am over here. So how do I describe a point? Let us say I measure theta here and I measure r here, the radius. So the vectorial description in terms of radius and theta is given by r cos theta I plus r sin theta j plus of course 0 k. So this is my E1, this is my E2, this is my E3, okay. So what happens? My dr is equal to del the vector del radius dr plus del vector del theta d theta, okay. So what is del r by del r? That is cos theta I plus sin theta j, okay. So del r by del r magnitude squared is 1, which is a1 square, and implies a1 is 1. What is del r by del theta? R comma theta, okay. That is equal to r times minus sin theta I plus cos theta j, okay, and therefore del r by del theta is equal to r square. That implies my a2 square, which implies a2 is equal to r. So what is my first fundamental form? For a circular plate, ds square is equal to 1 dr square plus r square d theta square, okay. So this is a1 square and this is a2 square. So you can now see that this a1 and a2 are functions or entities that convert the coordinate change, okay, to a length, change, to a change in length, okay. Very often the coordinate change or the coordinate is theta, angular, okay, and that has to be converted to a length. So that is accomplished by a1 and a2, okay. Time is running out, so I will close this lecture here and we will continue from here in the next class. Thank you.